Welcome back to the channel. Man, I'm behind on my videos. I've been wanting to do a part 2 video on the diesel engine balance job that I need to do. So you'll see that video upcoming. What I want to do is kind of reverse engineer the bob weight and then lighten the rods enough that the heavier pistons will work with that engine. So that's an upcoming video. But I decided to kick off a new series of videos on automotive electrical, automotive electronics. It seems to be where a lot of guys struggle. So, and that's been true with the hobbyist, and it's also been true in my career with fellow technicians. Electronics are the area of car repair that a lot of guys and gals just don't really excel in. So I'm going to do a series of videos on diagnosing, repairing, and overhauling automotive electronics, and try and be as informative as I can. So anyway, I wanted to start off by talking about wires, because that's probably the single biggest thing that I see is wiring repairs. You know, the component end of it's pretty cut and dry. You have a component that fails and you replace it. No big deal. You just unplug a connector, replace the component, plug it back in, and you're off and running. But what happens if you do that and it does not fix it? So then we get into the wiring issue. You've got an open or short or high resistance, and that can cause some guys to pull their hair out. So anyway, we're going to talk about wires a little bit. So wires are kind of like the circulatory system of the automobile. It's what sends voltage and current around the vehicle. And automobiles are particularly cursed with a 12-volt system, which means we're not starting out with a whole lot of voltage. So we make up for that lack of voltage by running more current to get the power that we need. Remember, voltage times current equals power. So if we have very low voltage, in order to get a high power number, we need lots of current. So with a 12-volt system, you're going to see larger conductors than you would with something like a 40-volt system, because we need that extra real estate to move the electrons to power our device, whatever it happens to be. That's why starter cables are so huge, and anything that draws a significant amount of current, for instance a rear window defogger, is going to have a pretty big wire running to it to make up for that lack of voltage. So the manufacturers have toyed with the idea of going to higher voltage systems, but higher voltage systems cause a risk of electrocution. Anything around the 40-volt mark and higher, electricity becomes dangerous, because the resistance of the human skin is low enough that with that voltage you can get enough current through the heart to stop your heart. So around the 40-volt mark is where things get dangerous. So there's been a lot of pushback, and I think before we'll see a 40-volt system, we might see some 24-volt systems. In fact, I think that you see some of those in big trucks and tractors. So it helps when you're trying to start a big diesel engine to have twice the voltage on hand. So, but anyway, what we're dealing with is mostly low voltage stuff. Occasionally you can run into starter issues and other issues with devices that pull lots of current, but typically in and around an engine you're dealing with low current stuff, so you're probably going to see something around a 14 or a 12 gauge wire running those components. And that can drop down, if you don't need a lot of current in the circuit, you might drop down to a 16 or 18 gauge wire. So there's some examples of those. And by and large, when you're working with wiring, what happens is the insulation fails to do its job. So copper Although copper is a pretty stable element, it can corrode if it's left open to the atmosphere, if it's exposed to oxygen, if it's exposed to road salt, if it's exposed to moisture. It can corrode, and typically with moisture it'll turn green. With oxygen it just loses its color, it gets a dull color. You can see this is still pretty shiny. One of the things about working on cars out here in the desert is we don't have a lot of moisture in the air, so we don't have to deal with as much corrosion as you would if you lived in some place like Buffalo, New York, or Cleveland, Ohio, where I'm actually from. So copper, the insulation on copper wiring is critical. This is where the problems arise. So when you're doing a repair, the two big things is we want to make sure that the copper is sealed from the elements when we're done. The other significant point is we want to make sure that the mechanical connection is solid. So the two components of a successful electrical or electric wire repair is the mechanical side of it and then the electrical side. So mechanical side is just the actual method used to attach those two leads, and then the electrical side is how do we seal it from moisture so that the electrons can travel through that connection. So we have to deal with that. So what I see a lot of, which is totally wrong by the way, we'll get into the tools here in just a second, but for now let me just strip this, and I'll strip this one. You can see that copper is not very clean. That would indicate a problem. So this insulation hasn't been doing its job. But for my illustration purposes, we'll leave that alone. So the simplest repair that I've seen and done, I've actually done this, is just to simply twist the wire together and then run a piece of tape over it. That's probably the simplest repair you'll see, but it's not really acceptable. Maybe if it's inside the cabin of the vehicle, it might be acceptable for a while. But under hood or under the vehicle, no way. This would be considered a temporary repair in that environment. So you wouldn't want to do something like this under the hood. Okay for a temporary repair, and I have done that for a temporary repair. But you just don't want to do that for a permanent repair under the hood because it's not sealed against the elements. So the classic repair that I employ under the hood is not much different. We just have to add a couple of steps to that. Once again, that wire is not clean. Let me go down a little further and see if I can find some clean copper. I think this wire's suspect all the way through. Yep, this wire's no good. Let's find another one. Let's try this one. Same thing. Much better. So the classic repair that I'll use under the hood is very similar to that twist and tape method that we saw just a few seconds ago, but what I'll do is I will twist. And then the next step is very critical. So this twist is the mechanical portion of this repair. But in order to seal it from the elements, I'm going to do two things. And the first thing I'm going to do is I'm going to solder it. So now we have a good mechanical connection by the wire twist, and we have a good electrical contact by the solder, and then we're still missing one step. Now we have to seal it from the elements. And to do that, I'm just going to employ some heat shrink. So this particular heat shrink has a sealer or glue that is on the inside of the plastic. So when you heat this up, it will actually adhere itself to the insulation and the copper. And you can do this with flame too. A cigarette lighter is something I like to use. You just have to be careful you're not around anything flammable if you're doing it. So this is a type of repair that I would do under the hood. And this is a much better repair than just the twist and tape method, obviously, because it's sealed. You can see the glue has oozed out. And once that cools off a little bit, that's going to be completely sealed against the elements. So no moisture could get in there, no oxygen can get in there. That repair is going to last a long time. So that's the best way to do a wire repair under the hood or under the vehicle if you want it to last. And it's the way I've been doing it for years and years and years. So there is another way to do it. You can use these notorious objects. But the problem with these is they don't seal. So while they give you a good mechanical bond to the copper when you crimp them, they're not sealed against the elements. They're not sealed from moisture. They're not sealed from oxygen. So these aren't a good idea to use under the hood or under the vehicle. They're probably okay if you're wearing a stereo inside the car, something non-critical. But you definitely don't want to use these butt connectors if you're repairing a circuit that's high current, like a blower motor or an ignition switch or something that's pulling a lot of current. Would be a bad idea. So if I'm going to use these, and sometimes I'm kind of stuck, and I'll show you a situation where you might have to use something like this. Let's say that I'm repairing this right here. So I had a wire that broke here, or maybe the insulation was cut, and I had to cut back that far to get the good copper. So this is obviously not going to work with the twist and heat shrink method. Just not enough there. So what can I do? Well, what I can do is I can strip that a little bit, and then I can take this butt connector and I'm going to turn this from an insulated butt connector into a non-insulated butt connector. And you could buy non-insulated butt connectors. That's something that you can purchase. But the problem is, if you go to your average parts store, you're never going to find them. So what I'll do is I will cut the insulation, being very careful not to cut myself. Should be enough. And we just want the center part of that rascal. So once we have the center part of that, what I can do is utilize a really good pair of crimpers. And you always want to line the seam of that butt connector up with the little protrusion on your crimpers, and then I can go ahead and I can put that in there, and I can crimp it. And then once I've done that, I can take a piece of wire and I can just go to the other side of it and do the same thing. Now, could I put a piece of heat shrink over that and shrink it down? Yeah, I probably could. But I'm not going to do that because I have a piece of heat shrink sitting here somewhere. Where would I do that? Oh, here we go. So I'm just going to slide the heat shrink up over that and shrink it down if I wanted to. But if it's a high current item, I'm going to go ahead and solder it. So solder this just like you would a wire. Just heat that thing up just enough so the solder will start to flow. And that gives me an extra level of safety on this connector. So I'll let this go down. Don't want to slide the heat shrink on there now because it would shrink down before I get it slid over. Once I get it cooled down, here we go. Now I can slide it up there. Probably should have chose one size bigger. Let's go on there a little bit more. Should be good enough. And there you have it. So when you're working with a very short stub of a wire, that's the way to save a connector so you could reuse it. So you always want to strip down till you see good copper. A lot of times if you have a wire that's been open to atmosphere for a long, long time, just like that wire that I stripped earlier, it was corroded, so that one's okay, that would work. But if I didn't like that, I'd have to trim it back a little further. So, alright. So when you're dealing with wires, wires have resistance. And the resistance is measured in ohms per foot typically. And that means if you're going to run a very long run of wire, which we typically all do with automotive stuff, unless you're dealing with a semi-trailer and running lights to the back of that or something outside of the scope of a typical automotive hobbyist. The longest wire runs we're going to see are probably, what, 20 feet maybe? That's about it. So typically we don't have to worry about the resistance of the wire too much, but be aware of that. If it's a really, really long run of wire, you might want to up the gauge of the wire just a little bit, because remember, we're only starting out with 12-ish volts. So if you're running a circuit to the back of your vehicle that's going to pull significant current, let's say a 12-volt wire in your 7-pin trailer hitch to charge the battery on your trailer, for instance. So you would run something a little bit bigger than you would normally think about running. So I wouldn't run 12 gauge in that situation. I'd probably pick 10 or something a little bigger. It's because that longer run is going to, by the time that voltage gets to the back of that vehicle, it's not going to be what it started out as. And you could see that. I mean, if you just turn a brake light on in a car and you measure the voltage at the brake light switch and then go back and measure the voltage right before the brake light bulb, it's going to be a little bit less, just because of the resistance of that wire and the connections too. Because everywhere there's a connection, there's going to be a little bit of a drop in voltage. So another good idea when you're doing automotive electrical is always have some dielectric grease, and every time you pull a connector out, smear a little dielectric grease on the blades and put it back together to keep it clean and keep it sealed. So very important. So you've made your repair. The next step is to make sure that that repair is going to last by anchoring it away from anything that might cut it again. It's amazing to me with modern cars how many times we're doing repairs because a wiring harness got up against something sharp or something hot, or when it was engineered there just wasn't enough provision for vibration and motion of a wire. You'll see wires degrade, insulation on wiring will degrade when it comes in contact with oil. This used to be a really big problem, not so much anymore because modern cars don't seem to leak oil as much as they used to. But if you go back into the 70s and 80s, you would have an engine with cork gaskets leaking oil onto wiring harnesses, and after 5 or 6 years of that, the insulation would be so compromised that it would literally just fall right off the copper. And that's where a lot of our wiring problems came from. So, you would want to repair the wire, but you'd also want to repair the oil leak in that situation. As I mentioned a few minutes ago, harnesses come in contact with sharp objects. We call that chafing. And modern cars have a big problem with this because modern cars have lots of wiring in them. Miles and miles of wiring. It's just incredible. I mean, we got modules all over the car and switches all over the car and lights all over the car and scads of sensors on the engine. And if a wiring harness isn't engineered properly, or if wherever it's retained, that retaining method doesn't work and it falls out of that and contacts something sharp, you can get chafing and it'll cut the insulation and it can short out and blow fuses. It can cut the wire outright. If it's on an engine, it can cause fault codes. So chafing is a big problem. A good way to find chafing, if you have a mystery code that you can't figure out what is causing it, is just to clear the code, put your scanner back on it, and just wiggle harnesses until the code trips again. So most scanners, you can go into a live function and you can actually monitor the code chart and start wiggling harnesses. And if you find the one that's shorting to ground or what have you, the engine may have to be running, of course, but if it's a live fault or a monitored fault, but you can just wiggle harnesses, and sometimes you get lucky and just wiggle the right harness, cause it to short to ground or open up and trip a code. Now you know you're close, and from that point you can just cut into the harness where you were wiggling it, and if you're lucky you can find that. See, I've mentioned oil, I've mentioned abrasion, and hot. So exhaust manifolds, exhaust pipes. I've seen wires melt against exhaust pipes, come out of the retainers, fall against an exhaust pipe, melt out, short out under the vehicle. I've seen wires get wrapped up in drive shafts. That's a fun one. Rips the harness out. That requires a lot of repair. Copper does something that has to be considered when you're engineering wiring harnesses, and that is it work hardens. So if you have a copper wire, I'm just going to steal this because it's got a butt connector, and that's exactly what I need to show this. So here we have a connector, and this is rigid. The butt connector is rigid. The copper wire is flexible. So let's say that this connector is bolted to the firewall, and this little pigtail is bolted or hooked to the engine. And as the engine moves back and forth, it's going to flex this connection. So if you just take this and it just move this back and forth like this, what happens is the copper work hardens, which means that it gets brittle the more you do this. And at some point over the life of that vehicle, what's going to happen is that connection is going to start fraying and breaking. And at some point, if it's a high current device, it might just outright melt and let go. So work hardening is a problem with anything that's in motion. We see it between an engine and an inner fender. We see it between an engine and a firewall. We'll see it in the pinch of a door, especially driver's doors, because they open and close more than any other door in the vehicle. So if you have a window switch or a door lock switch that stops working, chances are it's just a broken wire inside the driver's door pinch or the hinge, where that thing is just opening and closing constantly. And eventually the copper will work harden and start breaking inside that insulation. So if you ever have a situation where you think you have broken copper inside the insulation from motion, the easiest way to find that is just to grab the wire where you think it might be broken and just pull on it. If the copper is broken, the insulation will stretch, and you'll feel that stretch. And then you know it's broken, so you can go ahead and do that repair using a method similar to this, and you'll be up and running. I've seen inside door pinches, I've seen 5-6 wires break before the owner finally gets fed up with it and takes it in to get it repaired. And in that situation, I'll pull the harness completely out of the door, lay it out on the floor, and do that repair and put it back in. Or buy a new harness. If you have the new harness and it's not ridiculously priced, even better option. So, okay, we've covered oil, we've covered chafing, we've covered work hardening, broken wires. What else do we have to deal with? Strain relief. So when you're doing connectors, such as this. One of the nice things about the twist and tape method is you don't have to deal with strain relief because you haven't turned that connection into an immovable point. But if you have a soldered connection, or you have a butt connector, then you have to deal with strain relief. And the purpose of strain relief is to prevent the work hardening of the connection. So I'm just going to crimp this one, but I'm not going to solder it just to show this. But here we have a connector. And I'm going to go ahead and crimp this connector. I'll go ahead and solder it. It'll take a second. So now what we have is a connector hooked to a wire. The wire is flexible, but the connector is not. So if we left this like this, and let's say the disconnector's on the firewall, and this wire is bolted to the engine. As the engine rocks back and forth, eventually we'll work harden that and break off right at the connector. So how do we address that? Well, you need to provide some strain relief. So there's several ways you can do this. First, the easiest method is to find something you could zip tie that wire to, so when it moves, it's not moving the connection. That's one way to do it. If you don't have that option, then you can provide that strain relief in the connector itself. And the easiest way I've found to do that is just to use shrink tubing. That's never going to work. Next size up. So here's one way you can do it. So that's on there, but that's not quite going to be enough, I think, because even when that cools down, it's still going to flex. So what we're going to do is we're going to put another piece in there. It's a little bit bigger. And that should provide the necessary strain relief that we need. So as this bends, it's going to have kind of a staged reaction there, so it can bend and move around without breaking it right at the connector. So, and it's sealed, nicely sealed from elements. Not sealed at the connector, but once we get to the connector or connection, whatever this plugs into, let's say it's a spade, just put some dielectric grease on it and plug it in. Way to go. Okay. If I'm choosing 16, 18 gauge wire, that's going to be something for 5 amps or less. So tail lights, brake lights are probably okay. Injectors are 12 ohms a piece, they're less than an amp, so okay for that. Sensors on the engine, perfectly fine. You wouldn't want to do this with a headlight, you wouldn't want to do it with a blower motor. headlamps, incandescent headlamps or halogen headlamps typically pull about 7 or 8 amps each. So I wouldn't be choosing 16 or 18 gauge wire for that. I'd move up to 12 gauge or 14 gauge. So 14 gauge, I'm comfortable with 14 gauge up to about 10 amps. And 7 to 10 amps. It's a good idea to oversize a little bit, especially if you're working with headlamps, because you want them as bright as you can get them. So you don't want any voltage drop at the end of that. Same thing goes for blower motors, cooling fans, that sort of thing. So 14 gauge is probably okay. 12 gauge is probably a little better. Anything that's going to pull 15 amps or more, so say 15 to 25 amps, you're going to want to run 10 gauge wire. And you're going to make sure that everything is perfectly sealed to the elements and every connection is soldered and it's fused. Fusing, I always want to choose a fuse that's probably 30% more than the peak current of whatever device you're powering up. So if it's a blower motor, when you first turn it on, it's going to be a surge of current, and then it'll drop a little bit. And you want to figure out what that peak current is, and then add about 30% buffer to that. So if let's say your headlight pulls 8 amps, probably want to choose, let's see, 10 amps would be 20%. I'd probably go with a 15 amp fuse for an 8 amp headlight. And if you have 2 headlights, you'd probably bump it up a little bit more than that. So it would be a 30 amp fuse. You always want to make sure that if you dead short the wire, that there's enough current that can run through that wire to blow the fuse. So if you have a 30-foot run of 18 gauge wire, you'd want to make sure that if you just took that 30-foot gauge or 30-foot run of 18 gauge wire, and if you put one end of it on the negative battery post and one end of it on the positive battery post, the resistance of that wire, especially when it's hot, because as the resistance will go up as the wire heats up. So as the copper gets hot, the resistance goes up. So there may be a happy medium where this wire, a dead short of a 30-foot 18 gauge wire, would just sit there at 200 degrees, and if the insulation is really good insulation, it might be happy with that. So you'd want to make sure that at whatever current that is, at that resistance, that your fuse is low enough that it's able to blow at that current rating. So let's say that the resistance of a 30-foot section of 18 gauge wire at 200 degrees is 2 ohms. And if you do the math, that's 6 amps. So you want to make sure that you would have less than a 6 amp fuse on that circuit to protect it. So what else do we got? Oh, that's pretty much everything that I want to talk about on wiring. So I'm a fan of tape when it comes to taping up harnesses. So if I've got 4 or 5 wires together, I'm perfectly okay just taking black tape and taping those up. Split loom is okay as well. I'll use split loom if there's a chance of abrasion on something, or if I want a little extra protection from heat, I might slide them in some split loom and tape that up. But all the old cars from the 60s and 70s, they just used tape. They taped up the harnesses and made sure that they were not going to chafe against something sharp or rub against something hot, and it works fine. And I like it because it's a smaller bundle with tape, where if you put split loom around that, it just becomes like a snake swallowing a rat kind of syndrome, which I don't like. But it has its places. But you'll see me typically when I'm working on an old car, if I untape the harness, I'll retape it with black tape, just like it came from the factory, and just run it that way. So, have I covered everything? I believe I have. Yeah, I think I've covered everything on this one. So I'll figure out what I'm going to talk about in the next video. It's going to be automotive electrical as well, but I'll start getting into some other stuff. I want to cover relays and fuses and diagnosing sensors and all kinds of stuff, lighting. So I'm going to branch out. This will probably be 4, 5, 6 episodes that I'll be talking about automotive electrical. So, hey, thanks for watching.